Molecules, Compounds, and Chemical Equations Part 2. Today we're going to be looking at revisiting word equations, balancing equations, types of equations, specifically looking at combination reactions, decomposition reactions, combustion reactions, single replacement reactions, and finally double replacement reactions. Let's start out by reviewing some word equation translations. So all we're going to do here is read the equation that is given to us and translate it into a symbolic expression. Hydrogen combined with copper 2 oxide produces copper and water. All right, first thing that we have to remember here is that hydrogen is a diatomic. So when we represent that, that is going to be H2. Combined with is represented as a plus sign. Copper 2 oxide. All right, so we have copper with the Roman numeral number 2, so that means it's going to be Cu plus 2. Oxide is oxygen, and we're dealing with a pretty normal scenario with oxygen, so that is going to be O minus 2. So the plus 2 and the minus 2 are going to cancel each other out, which means this is going to be represented as CuO. Produces, which is an arrow, copper and water. So copper by itself is a metal, so that's just going to be Cu, and then plus, then the formula for water, of course, is H2O. And that's translating this particular word equation into a formula equation. Let's look at the next one. Carbon plus oxygen produced carbon monoxide. So carbon by itself is just going to be C, it's not a diatomic. Plus is going to be represented as, hey, a plus sign. Oxygen is a diatomic, so it's O, the subscripted 2, produced, which is an arrow, and then carbon monoxide. This is a binary molecular compound, so it's going to be a C and an O because it's monoxide, so one oxygen at the end. That is just the translation from the words to the formulas. Let's look at the next one. Magnesium metal and sulfuric acid combine to form hydrogen gas and magnesium sulfate. Okay, so magnesium metal is going to be Mg plus sulfuric acid we should know because we just reviewed how to write acids. So sulfuric acid is H2SO4, and you do need to memorize that. Combined to form is going to be represented as an arrow. Hydrogen gas, of course, is going to be H2 because it is a diatomic. And magnesium sulfate. It is worth taking a moment here to say to yourself, okay, magnesium is plus 2, sulfate is a polyatomic, that's SO4 minus 2. The plus 2 and the minus 2 are going to cancel each other out, so magnesium sulfate is going to be MgSO4. So again, this is another example of just taking a word equation and representing it as a formula equation. Now let's get into a review of balancing equations. This is all things that you should know how to do from your previous chemistry courses. So on this slide, we have 1, 2, 3, 4 equations to balance. So what I'd like you to do, we're going to go over the first one together, and then I'd like you to stop and attempt to balance the next 3 on your own. So we have Ca plus H2O yields H2 plus CaOH2. When balancing equations, I usually leave the oxygens and the hydrogens to the end. So if I look at this, I say, all right, 1 Ca here, 1 Ca here, because we assume there's a 1 right here. Okay, so the calciums are balanced. The next thing I'm going to go to is the oxygens, because hydrogens are listed in multiple places over on this side. So the easiest thing to go to is the oxygens. On this side, I have 1 oxygen. Over here, I have 2 oxygens because this 2 with the parentheses distributes through. So over here, I have 2 oxygens. I need these to balance, so I'm going to put a coefficient of 2 in front of here. So now that 2 is going to distribute through. So 2 oxygens, so then now this becomes a 2, so 2 oxygens, 2 oxygens, those oxygens are balanced. The last thing I need to do, because again, I have 1 calcium, I have to balance my hydrogens. And in a perfect world, because this is the last element that we're dealing with, This should be relatively straightforward. So 2 times 2, this gives me 4 hydrogens on my reactant side. How many hydrogens do I have on my product side? Well, I have 2 hydrogens right here, and I have 2 hydrogens right here, because remember this 2 distributes through. So on this side, I have a total of 4 hydrogens. So if I go back and I check one more time, 1Ca, 1Ca, 4 hydrogens total on the reactant side, 4 hydrogens total on the product side, 2 oxygens, 2 oxygens, this is balanced. Now again, what I'd like you to do is stop, balance the next 3 equations, and then check your work. Welcome back. Let's see how you did. I'm looking at my next one. I have copper plus oxygen gives me copper 2 oxide. All right, so 1 copper, 1 copper. 2 oxygens, ooh, 1 oxygen. I need to get my product side to have 2 oxygens. So I'm going to throw a coefficient of 2 in the front. So if that 2 distributes through, I have 2 oxygens, 2 here, 2 oxygens here. That's balanced, but now I got to go back and rebalance my copper. So this 2 means I have 2 coppers here, which means I have to throw a 2 in front of here, and now that is balanced. Let's go to the next one. 1 Na, 2 Nas. All right, so we got to deal with that. 2 oxygens, 1 oxygen. So I'm going to go ahead and balance the sodiums first. So I'm going to throw a 2 in front of here. So 2 Nas, 2 Nas. I have 2 oxygens right here. So, oh no, I should not have made that assumption that the sodiums were going to balance out automatically at the beginning, because I need a 2 in front of here. Because if I have 2 oxygens here, I need this to distribute through and this to be 2 oxygens. So what I need to do is very carefully erase that 2, erase this 2, erase this 1, and go back and fix this now. So 2 times 2, that gives me 4 sodium, and then I need a 4 in front of here. So checking one more time, 4 sodium, 2 oxygens, that is balanced. Let's look at the next one. 1 Fe, 1 Fe, 2 Brs, 3 Brs. All right, I need a common number between the 2 and the 3, and that would be 6. So I need to get 6 Br here, 6 Br here. So 3 times 2 will give me 6, and 2 times 3 will give me 6. So my bromine are balanced, but now I need to go back and balance my iron. So if I have 2 Fe right here, that means I need to throw a coefficient of 2 here. And again, I like putting the numbers over the top. All teachers have different manners and methods for balancing. This is just mine. You can use whatever you like, but this is the clearest picture that I get that something is balanced. So 2 Fe, 2 Fe, 6 Br, 6 Br. These are all balanced. Let's go to the next one. Again, what I'd like you to do is stop, balance these 4, play the video, check your work. Welcome back. Let's see how you did. Fe plus HCl yields FeCl2 plus H2. All right, I am going to look at this and I'm going to say 1 Fe, 1 Fe. Okay, so that's balanced. 1, 1. Going to leave the H's to the end. 1 Cl, 2 Cls. So I'm going to put a 2 in front of here. So 2 Cls, 2 Cls, that's balanced. Which leaves us to the hydrogens. So 2 H's here, and hey, 2 H's here. All good, all balanced. Oh, look, a combustion reaction is next. I have butane plus oxygen gives me carbon dioxide and water. Now, there's a very specific way of balancing combustion reactions, and you always start with the carbons first. So I have 4 carbons here, so I'm going to put a 4 in front of the CO2. 4 carbons, 4 carbons. Then I'm going to go to the hydrogens. I have 8 hydrogens as reactants. I'm going to put a 4 over here. 4 times 2 gives me 8. So now my hydrogens are balanced. The last thing I want to do is balance my oxygens. So 4 times 2 gives me 8. And then the 4 distributes through with an assumed 1, which is right here, which is 4. So 8 plus 4 gives me 12. So I need 12 oxygens over on the reactant side, so that means 6 times 2 gives me 12. And now this combustion reaction is balanced. Let's look at the next one. Na2CO3 plus HI yields NaI plus CO2 plus H2O. Looking a little nasty. Yes, it is, but let's take this slowly. I'm going to start with the sodium. So 2 sodium. I'm going to need 2 sodiums over here. All right, so that means my sodiums are now initially balanced. Now, since we have the iodine right here, let's go ahead and balance that. So 2 I's. I need 2 I's over here. So I'm going to have 2 I's over here. All right, so now this is balanced. And since I'm with the H's, why not? Let's look at the H's. So I have 2 H's here, and oh look, I already have 2 H's over here. So the last elements that I'm left with are the carbons and the oxygens. Well, if I look at my initial formula right here, I have 1 carbon, and I go over to the product side, 1 carbon. On the reactant side, I have a total of 3 oxygens. If I very carefully, with a deep breath and saying I can do this, I look over at the product side, I have 2 oxygens here, and I have that assumed 1 right here, so 1 oxygen here, which means I have a total of 3 oxygens on the product side, and this thing is balanced. So even though this problem looks complicated to balance, if you take your time and you're methodical about it, it should be pretty straightforward. Let's look at the next one. 1 Cu, 1 Cu, 1 carbon, 1 carbon, 3 oxygens. We have an oxygen here and 2 oxygens here. Hey, that's already balanced. We don't need to do anything to the coefficients here. We just leave it as it is. Last couple. We have 4 left here. So again, I'd like you to stop, try to balance these, and then check your work. Welcome back. Let's see how you did. All right, at the first one, I have 1 Pb, 1 Pb. Okay, I've got this nitrate ion, polyatomic ion right here. So this 2 is going to distribute through, which means I'm going to have 2 nitrogens right here, which means I need to have 2 nitrogens right here. So the nitrogens are balanced, but now I need to look at the oxygens. So 2 times 3, that gives me 6 oxygens. How many oxygens do I have over on the product side? Well, I have 1 here, I have 4 here, and I have 2 here. And that gives me a total of 7, which is not good. I don't want 7. 7, that's not going to work for me. I need an even number. When you get us into a situation where the number of oxygens on one side and the number of oxygens on the other side are not equal to each other, take a deep breath, erase everything, erase, erase, erase. Go back to your initial location of your oxygens, and what you want to do is double it. So very calmly, I'm going to put a 2 in front of the Pb, and watch what happens here. Okay, 2 Pb, coefficient of 2 Pb right there. How many nitrogens do I have total now? Well, 2 times 2 distributed through gives me 4, because remember, there's an assumed 1 right there. There's an assumed 1. So 4 nitrogens total. So I'm going to put a coefficient of 4 right here. So that gives me 4 nitrogens, 2 Pb. Finally, all right, how many oxygens do I have on the reactant side? Well, 2 times 2 is 4, times 3 is now 12. And let's see what happened to the other side. I have 12 oxygens on the reactant side. So 2 times the assumed 1 right here, that's 2. So let's put a little arrow saying, hey, I have 2 right here. 4 times 2 is 8. So now I have 8 oxygens right here. And oh, look, there's an assumed 1 right here. So that means I have 2 oxygens right here. 2. So 2 plus 8 plus 2 gives me 12, and the whole thing is balanced. So in situations where you have like an odd number of an element, try doubling everything. Sometimes that will work out. All right, let's look at the next one. H2SO4 plus KOH yields K2SO4 and H2O. Let's start with the potassiums. Potassium sounds good here. I have 1 potassium here, I have 2 potassiums here. So I'm going to put a 2 in front. So K2. Okay, so my potassiums are balanced. That's nice. All right, let's look at the sulfate ion. I'm going to see if I can keep this sulfate together. So SO4. As a whole, I have 1 SO4 here, and I have 1 SO4 here. So 1. Which leaves me on this side, how many oxygens do I have? Well, I'm not going to look at the oxygens from the sulfate. I've already accounted for them in terms of the polyatomic. But I do have 2 oxygens here. All right, I have 1 oxygen over here. Because remember, I basically got rid of the oxygens because I looked at balancing the polyatomic. So I have 2 oxygens on this side. So I'm going to throw a 2 in front of here. So now I have 2 oxygens on this side. And so those now balance, which leaves me to the hydrogens. I have 2 hydrogens here, and this 2 distributes through. I have 2 hydrogens here. So these together make a total of 4 hydrogens. If I go through this side, I've already taken care of the potassium. I got rid of the sulfate polyatomic. My oxygens are balanced over on the other side. But what I'm left here is 2 times 2, 4 hydrogens. So ultimately, this is now balanced. This was not an easy one to do. Let's look at the next one. NaHCO3, Na2CO3, H2O, CO2. I would love to think that I could just balance out the CO3s here, but that's not the case because I've got this random carbon over here, so I got to break everything down. Okay, so I have 2 NAs here, so I'm going to put a 2 in front of here. So 2 NAs, 2 NAs. That's balanced. All right. I now have 2 carbons total over here. How many carbons do I have on my product side? Well, I have 1 carbon here and 1 carbon here. So it now turns out that my carbons are balanced just by putting that 2 in front. Next, how many hydrogens do I have? Well, this 2 distributes through, so that means I have 2 hydrogens here. Hey, look, I have 2 hydrogens over here. So my sodiums are balanced, my carbons are balanced. Did that. My hydrogens are balanced. The only thing that's left is the oxygen. And now I'm going to pray that the oxygens work out evenly. So 2 times 3 gives me 6. I have 3 oxygens here, 1 oxygen here, 2 oxygens here, and 3 plus 1 plus 2. Hey, look at that, 6 oxygens. So again, if you label, if you're methodical, if you leave those oxygens and hydrogens to the end, it should work out okay. Last one. Al plus O2 yields Al2O3. Now it'd be so easy to say, all right, Al2, I'm going to throw a 2 in here. But I'm looking at my oxygens and I see that this oxygen is 2 and this oxygen is 3, which means we need that lowest common number that they'll both divide into, which is 6. So I'm going to do this really quick. I'm going to say there should be a 3 here that gives me 6. There should be a 2 here that gives me 6. My oxygens are now balanced and I can go back and finish balancing the aluminum. 2 times 2 is 4. So that means I'm going to need a 4 in front of here. So again, I just violated my rule. I did the oxygens before the aluminum, but I did take a moment to look through the entire equation and realize it would be in my best interest to balance those first before doing the aluminum. Let's look at some different types of equations. The first one we're going to look at is the combination reaction, which is also known as synthesis or direct combination, depending on your textbook. This is where 2 or more substances react to form one product. That's what we're looking for here. So symbolically, we represent this as A plus B yields AB. So a common reaction here would be a metal reacting with oxygen to form a metal oxide. So the example that I'm going to show you is magnesium plus oxygen, which we know is a diatomic, produces magnesium oxide. We know that magnesium is plus 2. Oxygen is typically going to be minus 2, so we're going to get MgO. And now that we've gone over balancing, we should look at this 2 oxygens here, put a 2 here, put a 2 here. And this represents a combination reaction. 2 reactants, 1 product. Decomposition reactions. One substance undergoes a reaction to produce 2 or more other substances. Symbolically, we would represent this as AB yields A plus B. Most commonly seen when a substance is heated. So a lot of times you'll see over the top of this, heat or energy or something like that. Common reaction here, a metal carbonate decomposes to form metal oxides and carbon dioxide. So for an example, solid calcium carbonate decomposes to produce solid calcium oxide and carbon dioxide gas. So let's start at the beginning. Solid calcium carbonate. All right, calcium is going to be Ca plus 2. Carbonate we know is CO3 minus 2. The plus 2 and the minus 2 cancel out. That is CaCO3. That's going to decompose, so that's an arrow, to produce solid calcium oxide. So calcium again is Ca plus 2. Oxide will be O minus 2. Those two cancel out. So CaO, and which will be a plus side, and then carbon dioxide, we can just look at that and say, well, that's CO2. And we look at this and we say 1 Ca, 1 Ca, 1 carbon, 3 oxygens, a total of 3 oxygens on the product side. Hey, that's balanced, and this does represent a decomposition reaction. Combustion reactions, rapid reactions that produce a flame. Something is burning. Commonly where a hydrocarbon reacts in air, which we're going to say oxygen, to produce carbon dioxide and water. This is something that you absolutely need to know. Common reaction, propane burns in air to produce carbon dioxide and water. So propane is going to be C3H8. We reviewed that from the summer assignment. Burns in air, we're going to represent that as oxygen, O2, to produce carbon dioxide and water. And we're going to balance this. We're going to say, all right, let's start with our carbons, 3 carbons right here. The carbons are balanced. Then always go to the hydrogens. 8 hydrogens. We're going to put a 4 in front of here. 4 times 2 is 8. And then we're going to balance the oxygens. So 3 times 2, that gives me 6 oxygens here. 4 times an assumed 1 right here, so that is going to be 4. 6 plus 4 gives me 10. So that means the coefficient here is going to be 5, and that is the balanced equation for a combustion reaction. Single replacement reactions. Absolutely need to know how to do these. When a more reactive metal or a nonmetal reacts with a compound to replace a less reactive metal or nonmetal. So symbolically, we'd say, all right, A is our more active metal. It's going to come in and it's going to kick out our less active metal. So B gets kicked out over here. And then A and C are going to hook up and form this new ionic compound. So calcium reacts with copper 2 nitrate to form calcium nitrate and copper metal. Calcium is going to be Ca by itself. Copper 2 nitrate. Copper is going to be Cu plus 2 because of that Roman numeral. The nitrate is going to be NO3 minus 1. We're going to cross those down and we're going to get CuNO3 2. I cannot express how important it is to make sure that you have the right formulas before you write the equation. If you put down the wrong formula, it will be impossible to balance and you will be weeping. No weeping. Arrow. Calcium nitrate. Calcium is Ca plus 2. Nitrate is NO3 minus 1. Again, we're going to cross. No positives, no negatives, no ones. So we're going to put Ca. That NO3 must be in a bracket. NO3, 2. And finally, we're going to have copper metal by itself at the end. So when I look at this, my nitrates are balanced. I'm going to look at that as a whole polyatomic. My calciums are balanced. My coppers are balanced. I am good. Let's look at one more example. Chlorine gas reacts with sodium iodide to form sodium chloride and iodine. Okay, chlorine gas will be represented as a diatomic. Reacts with sodium iodide. Sodium is Na plus 1. Iodide is I minus 1. So that's going to be NaI. To form sodium chloride, we know the formula for that, NaCl, and iodine, which is I2. Okay, so 2 chlorines here, so I need a 2 in front of here to balance those chlorines. 2 iodine over here, so I need a 2 in front of there. That'll balance my 2 iodines, and then 2 sodiums. This is balanced because a more reactive nonmetal will come in and kick out a less active nonmetal and form these products. Finally, double replacement reactions. When two compounds react in water, we'll typically find these in aqueous solutions, and switch cations to form new products. AB plus CD will yield AD and CB. So basically, the A is going to go with the D, and the C is going to go with the B. So that's where we see the AD and the CB. Over here, we are still listing, even symbolically, what we assume is our metal first and our non-metal second. Commonly form a precipitate or a solid as one of the products. Aqueous silver nitrate reacts with aqueous sodium chloride to form solid silver chloride and sodium nitrate. All right, aqueous silver nitrate. Silver is Ag. We're going to use the charge of +1. Nitrate is NO3 minus 1. So that means my first reactant is AgNO3. Reacts with is a plus sign. Aqueous sodium chloride. Na plus 1, Cl minus 1, that is going to be NaCl. To form is an arrow, solid silver chloride. Okay, for silver chloride, Ag's plus 1, Cl's minus 1, that means it's going to be AgCl plus sodium nitrate. Sodium is Na plus 1, nitrate is NO3 minus 1. Those charges are going to cancel, and we're going to get NaNO3. I look at everything, 1 Ag, 1 Ag, 1 NO3, keep the polyatomic together, 1 Na, 1 Na, 1 Cl, 1 Cl. Hey, those are balanced. I've got a balanced equation representing a double replacement reaction. So what did you learn? We revisited word equations and how to translate them into formula equations. We talked a lot about balancing equations and did a lot of practice. We looked at different types of equations, specifically combination reactions, decomposition reactions, combustion reactions, single replacement reactions, and finally a review of double replacement reactions. Need more help? Feel free to contact me. Have a great day.